to take a little time to talk about the operation of BitBlitting, bit block transfer operations. That used to be a more important topic in the old editions of my book, and also before we had WebGL. One reason I want to continue talking about it is that it's really crucial to understand how interactive systems actually work. But a lot of the interactivity that you see happening doesn't happen now from WebGL. It happens through the other operations that are going on within the browser and within other packages. But if you really want to understand what's going on up in the screen, the notion of BitBlt is really important. And it also will come up later when we talk about compositing and blending. What we'll be doing today is talking about manipulating single bits in the frame buffer, but if you extend that to the idea of a byte or an integer or a floating point number, the model is the same, just the how the arithmetic is carried out is different. And that'll be crucial for understanding compositing and blending, which is a part of WebGL. So let's just have a general discussion about writing into buffers. And as we said, WebGL doesn't have it, but we can do it in other ways through texture functionality. And then pretty much all of what we talk about today could be done within typically a fragment shader using the operations that are supported in a fragment shader, which lets you work on any pixel that you want. Okay, so bit block transfer operations became important because in terms of general graphics hardware, with a single instruction, machine level instruction, you could operate an entire block of bits instead of having a very slow operation where to change a block of bits, you'd have to execute one or more instructions for each bit in that block. Bit block transfer operations solved a lot of that problem along with the hardware that supported it. Now, what we need is a model for writing. And the model that we're going to use is going to be more general than the kind of writing that we've done up until now. Usually when we talk about writing something into memory, it's just a simple replacement operation. When you say x equals 2 or x equals y, you're talking about taking the memory location where x is and putting in the value of y or the value 2. And it doesn't really matter what was there before. That's why it's called replacement writing. But hardware allows much more interesting and flexible operations. And that's what we want to talk about. So first let's talk about a model that allows us to work with blocks. So let's think of it this way, and let's not worry about distinguishing between GPU, CPU. Let's just assume that we have this enormous block of memory, and part of it is the frame buffer. By that I mean that this part of it is always going to be displayed out on whatever your display device is. And what I'm going to do is have another block of pixels, typically generated by my program, and it's going to affect an area of its size in the frame buffer or partially in the frame buffer. And that's a writing operation, a generalized writing operation of a block. Okay, now what are the ways that I could write? Well, that we're going to look at for now as a bit by bit or perhaps pixel by pixel operation, which will happen for every one of the bits or pixels in this source block. This is generally called a source, and where you're putting it is called a destination. Now the model that we're going to use is a little bit more general than the replacement model that you usually use. See, the replacement model says, okay, given a source bit or a source pixel, all I'm going to do is put it somewhere in the memory. So I could have the idea of writing a pixel or writing a bit, but that's very, very simple. Let's take a little more general approach and say, what if before we put something into the destination in memory, that I read the value that's at that location first and then do some operation, either arithmetically or logically, between what I read there and use that to form the new destination value as some combination of what I read and the source value that I was provided. Now, if we do this on a bit by bit basis. See, later, as I said, we'll do this for blending, where these will be pixels or integers. But to understand what's going on, think of these as bits. So I'm reading a bit, and then I'm writing a bit out at a very low level. Now the question is, how many ways can I do that? And if you think about that, there's exactly 16. And the reason is that for every value of S, which is going to be 0 or 1, and D, which is going to be 0, 1, we're only dealing with bits, you have a table with 4 rows in it, okay? All the possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. Now, how many destination values can you get to fill the right side of that table, which we'll see in the next slide? Well, the answer is for every row in there, I have 2 possible values to put in, 0 or 1, but there are 4 rows. So I have 2 to the 4th possible ways that I could define the function that goes on in this block. And if you've done anything at the machine level or assembly level, then you see that these are the standard 16 logical operations that you can do between 2 bits. But since these have a visible effect, you're going to see the result. We call them writing modes. And so here they are. So here's the 4 possible values of S and D. And you have 16 possible functions for what they produce. Now, I'm going to number them by, if you read down least significant to most significant bit, I can number them this way. So this would be 0, this would be 1, this would be column 2, and so on until they're all 1s, and then this is column 15. Now, of these, most of them are not particularly important, although you could say, if you interpret, say, 0 as black and 1 as white, you could say that column 0 is the right operation of clearing the bit. It's always making it black. 15 would be setting the bit, always making it 1 or white. But the most interesting ones are the 3 that I have here in red. Replacement is 3. It says, look, I don't care what was there. D doesn't matter. I'm going to put in whatever S was, so I just copy S into this column. So writing mode 3 is the standard familiar replacement write. Oring them together, saying, hey, what I'm going to put down there is it's only going to be white if both the source and the destination are white. Otherwise, it's going to be black. That's called the OR writing, which is mode 7. The most interesting one, though, is mode 6. And if you look at that function, it's the exclusive OR function. It's 0 if both S and D are the same, and it's 1 if S and D are different. Okay, now it's interesting in a number of ways for what we can do with it, which I'll show you in a minute. But it's also interesting in the sense that if you go back here, you cannot implement exclusive OR except by actually reading and comparing these 2 things. It's much more, it's a little more hardware-wise difficult than simple replacement. Right. Okay, but let's look at exclusive OR here, because that's the one that's most interesting, and see what we can do with it. Well, the first thing to notice is that if we talk about the operation of exclusive OR and use this OR, this plus with a circle in to denote it, it turns out it undoes itself. And suppose I do this on a block, meaning that I do it for every bit in the block, for corresponding bits in the source and the destination. I compare them and I do it with one operation. Exclusive OR has and let's think of this as a menu and a piece of what we see, a piece of the frame buffer. Now, why do I do it this way? Think what happens when you do a pull-down menu or a pop-up menu in some interactive application. It gets drawn over what you already have, and then when it goes away, you restore what was originally under that menu. Well, how do you do that? Well, one way is that you take the block of memory corresponding to where that menu is going to go in the frame buffer, and you put it off screen somewhere, and then you bring it back when you're finished using the menu. That's swapping. You swap what's there with something off screen, then you do another swap, and you always have to have, as standard swaps, have some extra memory to do that, which is off screen. But let's look at this alternative using exclusive OR. If I exclusive OR the menu with that area of the screen and put that onto the screen, I'm going to get something which looks a little weird, but I'm immediately going to then take that and exclusive OR it again with the menu. And exclusive OR has the property that if you do S exclusive OR M exclusive OR M, exclusive OR S, excuse me, you get M. So now you've done the swap. You now have M on this display. And now if you exclusive OR that M with S again, the two S's cancel out. The two M's cancel out. Exclusive OR it with M again. The two M's cancel out and you're back to S. So you've actually swapped the little area of the menu that's stored somewhere with the screen, and now if I want to undo it, I just go through these three operations again. Now, what's the advantage of this? You don't need any extra memory. Remember, if you're going to swap X and Y, you have to put X in a temporary location, then put Y into X, and then get Y back from the temporary location. This is doing it in place. So with three exclusive ORs, you do an in-place swap, and that's a powerful, very, very fast operation that has a long history. It goes back to the days of people were trying to minimize the number of registers in some very old hardware, and they could not use an extra register if they used exclusive OR. People who built terminals discovered this operation, and they actually got away with patenting exclusive OR. And for the application that I'm going to show you next, which was just an absurdity in that all computer scientists knew about exclusive OR. All programmers knew about exclusive OR, but the patent office didn't. So anyhow, here's an example, a different example using exclusive OR. Suppose you're moving a cursor around the screen, and there were some very early tests I remember with Commodore hardware where people recognized, looking at where the time was spent by the CPU, that the CPU, this is pre-GPU days, was spending half its time tracking the cursor, not doing anything productive. But what happened was that they needed to do this kind of swapping, and as the cursor was moving interactively, it just ate up your CPU time. So people said, well, let's try exclusive OR. So what you can do now is, see, it's the same problem as with menus. As you move this little cursor around, it covers up an area of the screen, but when I move it somewhere else, you've got to have saved somehow that yellow part of the triangle in the background and return it. But if you do it by exclusive ORing the cursor in, then when you move the cursor, you do another exclusive OR to where it presently is. That returns the screen to what it looks like, to what its state before the cursor was there, and then has the cursor in the new position. And you can actually see on some hardware implementations that technique is still used. That you can see that when you exclusive OR the cursor, and the cursor, if it's just a black and white, say crosshairs, can look a little weird when it's on top of some black and white pattern, but it makes it very, very fast to move the cursor around. So that patent thing, I guess, has gone away because you don't hear about it anymore. But there was a time when the X terminals we had were from a company that was actually paying to use the patent to move the cursor around. Okay, now let me give you one more related example of that, and that's rubber banding lines when you're doing some interactive activity. So, for example, a rubber band line is suppose you're trying to draw a line interactively. So a typical way you do that is you click at one spot, and then as you move your mouse, the line is being drawn out with that first point fixed, and then when you get finally to where you want to be, so it keeps redrawing the line to wherever the mouse is at that present time. And then when I click again, then the line is fixed in place. And then as I go along in time, these lines are automatically being erased. Well, if you've been following what we've been saying about exclusive OR, and I say, well, how do you do that? The answer is you exclusive OR the temporary lines to the screen. So when I'm drawing this one, it's exclusive ORed on. Then when I move, I do an exclusive OR to where it was, which brings back the background and whatever objects were there under it. Draw the line in the new position with exclusive OR. When it moves, exclusive OR again. And then when I'm finally finished and I click on this, then you draw a line using replacement mode to draw that line on top, not interacting with the things underneath it. So it's a very powerful technique. It's automatically included in or used in virtually every interactive application that you're going to see. It's just that generally we support those things in WebGL by using HTML or something that runs with HTML and not having to program this ourselves. Although you will see applications where you'll want to do exclusive OR kind of calculations, and again, that'll be done within the fragment shader. Now let's keep this as background. We'll come back again when we talk about compositing, and now we're going to turn to looking at texture mapping.